Welcome dear learners. We are continuing Unit 3, Introduction to Nanomaterials. The title of the present module is Metal Oxide Nanoparticles Part 2. The contents are characteristics of metal oxide nanoparticles in a revision mode, silica nanoparticles, synthesis and properties, titania nanoparticles, its synthesis and properties, and applications of metal oxide nanoparticles. So, in the previous module, we have discussed some things, some important parameters about the metal oxide nanoparticles. And we are now refreshing the important characteristics of metal oxide nanoparticles. So, the characteristic features of metal oxide nanoparticles are familiar to you. Before entering into more details of representative examples like silica, titania, etc., we are just refreshing or revising the common, most important characteristics of metal oxide nanoparticles. First one, metal oxide nanoparticles exhibit unique characteristic properties due to their small size, large surface area, and distinct physicochemical characteristics. The nanoscale dimension is a characteristic feature. Their size of the metal oxide nanoparticle lies in the range of 1 to 100 nanometer. This leads to quantum confinement effect in them. Surface area, the metal oxide nanoparticles are associated with a very high surface area and hence surface to volume ratio. Stability is another characteristic feature. Generally, metal oxide nanoparticles are chemically stable due to resistance to oxidation. The metal oxide nanoparticles exhibit some redox activity. That means they can undergo redox reactions, oxidation reduction reactions. Characteristic examples include CEO2, Fe3O4, etc. These points we are discussing as a revision because we have considered all these properties more detail in the first part of metal oxide nanoparticles. Crystallinity, metal oxide nanoparticles exhibit different crystalline phases and different crystalline phases have distinct physical as well as chemical properties. Band gap tunability is another characteristic feature. Metal oxide nanoparticles, most of them exhibit their band gap tunability, that is band gap are tunable by size. Hydrophilicity is another characteristic feature of metal oxide nanoparticles. Functionalization or ease of functionalization, metal oxide nanoparticles can be surface modified with organic molecules, polymers, biomolecules, etc. This will enable further specific applications. Now, we just went through different characteristic features of metal oxide nanoparticles. And coming to today's discussion, we have focused two important nanoparticles, metal oxide nanoparticles, for our discussion in this module. First of all, I am taking silica nanoparticles. Before entering into silica nanoparticle, a question arises. Is silica a metal or non-metal? Absolutely, silica is a non-metal oxide nanoparticle. Silicon is actually a non-metal. So, we are discussing non-metal oxide nanoparticle silicon dioxide in this discussion because we have to make some comparative features, etc. So, we are considering silicon dioxide nanoparticles. Silica nanoparticles are nanostructures composed of silicon dioxide, that is SiO2, with the size typically ranges from 1 to 100 nanometers. Silica is optically transparent in the visible region. That means in the visible region, they will transmit light completely. That is, silica appears to be transparent. You know the transparency of glass. The glass is also made up of silicon dioxide. Silica nanoparticles have several characteristic features. They are characterized by high surface area. They are biocompatible. That means they will not create any toxic effect to living cells or biological tissues. They have versatility in functionalization. Different kind of functional group can be incorporated onto the surface of the silicon dioxide nanoparticles. These silica nanoparticles have some cavities in it. That means they have a porosity also. So these are various characteristic features of specifically the silicon dioxide nanoparticle or silica nanoparticle. Now we are discussing the synthesis of silica nanoparticle. You know there are several methods for the synthesis of metal oxide nanoparticles. And coming to silicon dioxide nanoparticle, the most important synthetic procedure is the sol-gel method. The sol-gel method we adopt for the synthesis of silicon dioxide nanoparticle is known as Stauber process. This is because this method was developed by the scientist Stauber. In this sol-gel synthesis, which is a most widely used method, we get monodisperse silica nanoparticles. That is, particles of uniform size we will get by the Stauber process. The Stauber process or the sol-gel synthesis of silica nanoparticle involves the hydrolysis and condensation of a silica precursor. In most of the cases, the silica precursor used is TEOS, that is tetraethyl orthosilicate. TMOS, tetramethyl orthosilicate, is another alternate, but in many cases we are using TEOS as the precursor to prepare silicon dioxide nanoparticle by sol-gel process. This TEOS or tetraethyl orthosilicate is dissolved in alcohol solvent and mixed with alkali, or this dissolution is performed under alkaline conditions. Tetraethyl orthosilicate in water undergo hydrolysis. Whenever you are adding some base or basic conditions, this tetraethyl orthosilicate, abbreviated as SiOR 4 times, is undergoing hydrolysis. The hydrolysis produces SiOH 4 times. That is, during the hydrolysis, the OR group present in tetraethyl orthosilicate is replaced with the OH group. So this is a base catalyzed reaction, a base catalyzed hydrolysis, and a basic medium is required for this hydrolysis. So this OR group is converted to OH group and you are getting the last compound SiOH 4 times. That compound is called silicic acid. Silicic acid undergo polycondensation forming siloxane bonds or SiO-Si bonds, and this polycondensation leads it to the formation of ultimate silicon dioxide or silica nanoparticles. The polycondensation happens because SiOH molecule, SiOH 4 times contains so many OH groups around the silicon. The OH group in first molecule may condense with the OH group of the second molecule by eliminating water. This leads to polycondensation. Polycondensation results in the formation of siloxane bonds. Finally, that is converted to silica nanoparticle. Second method used for the preparation of silica nanoparticle is microemulsion technique. A water in oil microemulsion, you know emulsion is a liquid colloidal system. A water in oil microemulsion system is used to control the size of the silica nanoparticles. Here in this method, tiny droplets of water are dispersed in an organic solvent, stabilized by surfactants, and the silica precursor, here also tetraethyl orthosilicate, is added to the aqueous phase. Hydrolysis and polycondensation reaction takes place within the water droplet, which ultimately leads to the generation of silica nanoparticles. Flame synthesis is another method used to prepare silica nanoparticles. This method involves a vapor phase hydrolysis of silicon containing precursors, preferably silicon tetrachloride, in high temperature flame. Vaporized silicon tetrachloride reacts with oxygen and hydrogen in the flame to form silica nanoparticles directly. This is the reaction which enabled the formation of silicon dioxide nanoparticle during the flame synthesis. That is, SiCl4 on reaction with hydrogen and oxygen from the flame, SiO2 directly obtained and HCl is eliminated as a side product. Now we are discussing the properties of silica nanoparticles. Size and morphology is the first part of our discussion. The size ranges from few nanometers to several hundreds of nanometers. Shape is typically spherical, even though some other morphologies are also possible. But keep in mind the fact that in most of the case, the silica nanoparticle appears to be spherical in shape. Now, the chemical stability of silicon dioxide or silica nanoparticles. The silica nanoparticles are chemically inert under physiological and mild acidic acid as basic conditions. But the presence of alkali, that is high pH, that is alkaline environment, may cause dissolution of the silicon dioxide nanoparticles. That means silicon dioxide nanoparticles are stable under ordinary conditions, ordinary pH, but strong alkaline condition may dissolve it. Next characteristic feature is the biocompatibility. The zinc oxide nanoparticles will not create any toxic effect to living cells or living tissues. That means the silicon dioxide nanoparticles are biocompatible. Now we are discussing the thermal properties of silicon dioxide nanoparticles. They have low thermal conductivity. This low thermal conductivity enables their application in insulating materials. They have high thermal stability. They are stable, they are thermally stable up to moderately high temperatures. Another characteristic feature is hydrophilicity. The surface of silicon dioxide nanoparticle is hydrophilic. This is because the surface of the silicon dioxide nanoparticles may have some OH groups or hydroxyl groups. This hydroxyl group can enter into hydrogen bond with the water molecule. So, silicon dioxide nanoparticles exhibit hydrophilicity. Now, we are going to discuss some additional information related to characterization of nanomaterials. This part we are going to discuss is not mentioned in your syllabus, but this part is highly useful as far as the nanomaterial science and nanotechnology is concerned. In coming very few slides, we are mentioning about characterization of nanomaterials. Characterization of nanomaterials. Suppose you are preparing a nanomaterial in the chemical laboratory. You know the fact that the nanomaterials are not visible with the help of your naked eye. So, with the synthesized material, you are unable to say about its actual size, about its morphology, shape, etc. In that circumstance, we require some characterization methods. In order to see small particles, we are commonly using microscopes. But the common microscope cannot show the nanoparticle because nanoparticles are very small to see through the common or simple microscope. In such a circumstance, we are using some special characterization methods. There are so many characterization methods to study, to follow up nanomaterials, and electron microscopic methods are most popular characterization methods of nanomaterials. Electron microscopy methods. Electron microscopy methods utilize high energy electron beams to image the nanoparticles. That is, in every electron microscopy method for the characterization of nanomaterial, there is a high energy electron beam which is produced from an electron gun or electron generating source, etc. That high energy electron beam falls on the surface of the nanoparticle and helps in imaging the nanoparticles. There are two most popular electron microscopic methods for the characterization of nanomaterials. They are scanning electron microscopy, abbreviated as SEM, and transmission electron microscopy, abbreviated as TEM. So, SEM and TEM are two most popular electron microscopy methods to study size, morphology, etc. of a nanomaterial. Now, the principle of scanning electron microscopy. The scanning electron microscopy uses a beam of high energy electron to scan the surface of a sample, to study the surface of a sample. The interaction between the high energy electron beam and the sample surface generate signals that provide detailed images of the sample surface. So remember, scanning electron microscopy helps in imaging the surface of the nanoparticle. The second electron microscopic method, which is more powerful than scanning electron microscopy, and this technique is transmission electron microscopy or TEM. Transmission electron microscopy again uses high energy electron beam, and that electron beam transmitted through ultra thin material sample. The interaction of this electron with the sample produce an image based on the difference in density as well as thickness of the sample. This transmission electron microscopy has several modifications like as high resolution transmission electron microscopy, etc. This kind of characterization method you can study more detail in your higher classes. And for a representation, I am showing a transmission electron microscope image of silica nanoparticles we have just discussed now. The TEM images of a sample of silica nanoparticle appears like this. You can see the spherical shaped silica nanoparticles. In a TEM image, there is a scale bar at the bottom portion of the diagram. This length represents 140 nanometer. So, whenever placing this scale bar on each and every particle, it is very well clear that the particle size is in the range of 100 nanometer. From this image, it is clear that the particles are of nearly same size. The particles with the same size and shape are said to be monodisperse. So, these are the images, the TEM image of nanoparticle which is prepared by the Stober method. So, these are some additional informations which support your learning. Characterization of nanomaterials by electron microscopy. There are so many other characterization methods like spectroscopic methods, thermodynamic methods, etc. That you can study in your higher classes. We are continuing with another kind of nanomaterial, another oxide nanomaterial, that is nothing but titanium nanoparticle. Titanium is a metal, so titanium nanoparticle represents metal oxide nanoparticle. Titanium nanoparticles refer to nanoscale particles of titanium dioxide. So, titanium is TiO2. Titanium nanoparticles are TiO2 nanoparticles. They exhibit unique optical, physical, photocatalytic properties, and titanium nanoparticles exist mainly in two crystalline phases. The two crystalline phases are anatase phase and rutile phase. That means titanium dioxide can exist as anatase TiO2 and rutile TiO2. These two are crystalline phases. These two crystalline phases have different physicochemical properties. Now we are discussing synthesis of titania nanoparticles. The first procedure, as usual, the most common procedure, that is sol gel technique. Titanium precursors like titanium isopropoxide are hydrolyzed and condensed in a controlled manner to produce titanium dioxide nanoparticles. The second method of preparation of titania nanoparticle or titanium dioxide nanoparticle is hydrothermal synthesis. Precursors react under high temperature and high pressure to produce well-defined titanium dioxide nanoparticles with controlled morphology. Third method we are adopting for the synthesis of nanoparticle, titanium dioxide nanoparticle, is the popular chemical vapor deposition or CVD method. A gaseous titanium precursor is deposited on a substrate and decomposed to form titanium dioxide nanoparticles. We are discussing properties of titanium dioxide nanoparticles. UV absorption is a very important characteristic feature. They will exhibit strong UV absorption from UV region, making it ideal for photocatalysis as well as UV blocking agents. Photocatalytic activity depends on their ability to absorb UV radiation. TiO2 generate electron hole pair or excitons when exposed to ultraviolet radiations. They can undergo some redox reactions that enable photocatalytic activity. Biocompatibility is another characteristic feature of titanium dioxide nanoparticle. They are generally considered to be non-toxic and safe for human use. Now we are discussing the applications of metal oxide nanoparticles. This is the last part of this module. We are entering into the generalized applications of metal oxide nanoparticles. They have wide varieties of applications and some promising applications of metal oxide nanoparticles are here. Many metal oxide nanoparticles are useful as photocatalyst. That is, the first application is in photocatalysis. They are useful in energy storage and conversion. For instance, photovoltaics and solar cells can incorporate metal oxide nanoparticles to improve their efficiency. Sensors, many metal oxide nanoparticles can be used in sensor development. Biomedical applications like imaging, targeted drug delivery, etc. are another category of applications of metal nanoparticles. Now, antibacterial and antiviral coatings can be developed from metal oxide nanoparticles. Catalysis is another application. They can be used in preparation of selective high performance solar cells. Water purification is another important application of certain metal oxide nanoparticles. Electronic as well as semiconductor devices can also be developed from selective metal oxide nanoparticles. In general, metal oxide nanoparticles exhibit several characteristic features and enormous applications in diverse fields. That's all about the discussion on metal oxide nanoparticles. Have a nice learning experience. Thank you.